Do you have any questions about last session?
I was curious if we considered GANs a subset of reinforcement learning or vice versa, or if they are just distinct algorithms.
Uh, they are distinct algorithms. So here you have unlabeled data, but here you have data, okay? When we go to reinforcement learning, you have environment that you interact with, and then the type of data that you're gonna have is gonna be different. Over there, your data, actually your decisions are gonna have impact on the data that you're gonna see.
Yeah.
And it's gonna have a sequential nature.
Okay, that makes sense.
And the data are not gonna be IID anymore, okay?
Yeah, because the things that you do give you different feedback.
Yes. So you can think of GANs as the inverse. That's actually a good idea to think about it this way, is as the inverse of what we have been doing so far. For instance, if you were doing image classification, you had an image and then you would put it through a classifier and that would give you the class. Now you can go the reverse route. You give it a class and you want to generate images.
Yeah.
So you can think of it as a one-to-many mapping, or you can think of it as learning the underlying distribution. It has many applications and you're gonna see it. We are gonna do GANs for a while, okay?
Thank you.
Any other questions? Okay, perfect. In that case, let's get started. So last session, we stopped here with conditional GANs, and we saw that it's a simple extension of regular GANs, not conditional or unconditional. So throughout, actually, I had in mind to separate conditional GANs from unconditional GANs to have two separate topics. But I thought it's a good idea to go back and forth between them because you're going to see the applications when you do conditional GANs. And then we are going to do some improvements on the objective function, on the neural networks that we use, etc. Okay, so it's a better idea to go back and forth between them. Now, one application of GANs in general is that you can actually use them to learn representations. So somebody gives you unlabeled data, and then you want to summarize that data in a lower dimensional representation vector. Okay, it's hard to work with images that are 256 by 256 by 3 channels. That's high dimensional. So it's a good idea to have a lower dimensional representation. But we don't want to do it in a supervised fashion. We want to do it in an unsupervised fashion. We don't want to have any labels. And let's see how far we can push that idea. The idea is that you're going to use deep convolutional GANs, DCGANs. So the idea is that you want to go deep. Okay, the previous papers that we covered, they were shallower. They were not as deep. And if you notice, the type of data that we were working with was MNIST or CFAR10. These are much easier data sets compared to Imagenet. So now we want to move towards Imagenet slowly and learn our representations from that data. But GANs are not stable. If you have ever tried to train them, they are not stable. And whenever something is unstable, maybe you need to change your neural network. Basically, maybe you need to change your prior. Maybe you need to change your loss function. Maybe you need to come up with better training strategies, etc. So these papers said I'm gonna try to change the architecture and do a lot of trial and error on the architecture. And they are kind enough to share with us their findings. For the architecture, these are the guidelines. There is no mathematical reason for why they work, or there is not much intuition. It's just trial and error. Change your configuration, train your GANs, see it converges or no. Do one change at a time until you come up with a neural network that converges. So what are the guidelines? These are the final lessons. If you have any pooling layers in your discriminator or the generator, replace them with strided convolutions. So pooling layer is usually used to reduce the resolution of the image from one layer to the next. It says that, and pooling layers they don't have any parameters, so they don't add parameters to your network. But the strided convolutions do. If you set the stride of a convolution to be 2, you're reducing the resolution by 2. This is for the discriminator. For the generator, you need to go the other way around. You want to increase the resolution until you reach the resolution of your images. And that's gonna be called fractional strided convolution. I'm gonna explain this, so don't worry about it. I'm gonna give you the exact mathematical formula for it. We know that batch norm is useful when we are doing classification or discriminative tasks. Let it be for languages, let it be for images. They said, okay, go ahead and use batch norm in the generator and the discriminator. So both of them use batch norm. If you have any fully connected hidden layers, just remove them from your architecture. Okay, they add too many parameters, and because they are fully connected, they are much less efficient compared to convolutions. So let's just remove them. Use ReLU as your activation function for all of your layers, except for the last one. For the last one, you're going to use a tanh, and the reason for that is your images are usually from 0 to 255. These are the numbers that are going to show up as your pixel values. If you normalize that to be in the interval from -1 to 1, then your neural network, that's going to be bounded from -1 to 1. You want your neural network to be bounded, the output of your neural network to be from -1 to 1. That's why you're going to use a tanh. And then use leaky ReLU as your activation in the discriminator. So see, some of them are for the generator, some of them are for the discriminator. Maybe for some of them we have intuition, for some of them we don't, but this is coming out of a lot of experimentation, a lot of trial and error. The question is, why not rescale to 0 or 1 and use sigmoid? You could do that. You could use from either -1 to 1 or from 0 to 1. That part should be fine. Does that answer your question?
Yeah, thanks.
Okay, perfect. The discriminator, the architecture is very similar to the generator. So the generator is going to go from left to right, and the discriminator is going to go from right to left, okay, of this architecture. But let's focus on the generator. The discriminator we have plenty of experience with, but the generator, how are we going to go from a vector that is 100 dimensional to an image, which in this case is 64 by 64 by 3 channels. So how do you go? The first step is project and reshape, and project in deep learning is just matrix vector multiplication. So you're going to multiply a vector that is 100 dimensional by a matrix that is 100 dimensional by a multiplication of 4 by 4 by 10,024. That's going to give you a vector. It's a very long vector. And then you're going to reshape it. You're going to turn that into a tensor. So a vector has dimension 1, a tensor is going to have dimension 3. 1, 2, 3. Then you're going to do a bunch of convolutions. So we said we are going to do fractionally strided convolutions. So you're going to do a bunch of convolutions, and each fractionally strided convolution is going to increase the resolution. So you're going to increase the resolution from 4 to 8 to 16 to 32 to 64. And this part, changing the dimension from 1024 to 512, for instance, you can do that with matrix multiplication. Okay, the resolution, you take care of it using convolutions, and this is just matrix vector multiplication. But if you look at this figure from right to left, you're gonna notice that this is just a simple convolution with a stride 2. If you go from right to left, you take a window, and then and this is probably a window of 3 by 3 or even 2 by 2. And then you collapse that window into a window that is 1 by 1, into 1 pixel. So there is going to be an addition over, I don't know, if this is this is actually a 5 by 5 convolution. So you take a window that is 5 by 5, you do a summation over all of those vectors after multiplying by correct dimensions to change from dimension 512 to 1024. And then you just add them up. That convolution, the deconvolution or fractionally strided convolution, is going the reverse route. And we know that we needed to do reverse route all the time. Why is that? Even when we were doing usual convolutions, we needed to do the reverse route because we needed our gradients. Okay, that was back propagation. So the convolution, actually fractionally strided convolution, is the derivative of a usual convolution. So it's a backward pass. We know about it, but we have never seen the formula for it. So what is the formula? You want to know the pixel value at this location, at location X and Y. There is going to be some convolution going on. There is some addition going on. You have some input vectors that are lying here. These are, because they are vectors, this X here is now 1024 dimensional. You multiply it by a matrix, and the outcome is going to be 512 dimensional. And then you need to add them up. The problem is, because you're dividing by your stride, this is fractionally strided, many of these values, actually some of these values, they are not going to be integers because you're dividing by, I don't know, maybe 2, because your stride is 2. Some of these values are not going to be integers. You just ignore them. They are not going to be part of your summation. Okay, you just ignore them because they don't exist. There is no such a pixel at your input. So you just ignore it. That's fractionally strided convolution. And how is it related to the backward pass? How is it related to the derivative or the gradients? Let's take a look at the forward convolution. So now you have a convolution. You're going from right to left. For forward convolution, you want to know the pixel value at maybe this location. That's basically a vector. Each pixel is a vector. And this is going to have a dimension of 1024. You take a window that is 5 by 5, or it could be 3 by 3. You have, in this case, 9 matrices. And then you take your X, and where the stride is going to come in, the stride is going to come in here, because then you're jumping from one portion of your image to the other portion. You're jumping by step sizes of 2. Okay, perfect. So that's a forward convolution. That's basically a convolution. It's a 3 by 3 convolution. Now we want to take its derivative. We want to know the derivative of loss with respect to X. And how is it related to the derivative of loss with respect to Y? First of all, let's rename this to be X prime. So, and let's compute X. X is going to be X prime minus I divided by S plus 2. And this is exactly what you had here by renaming X to be X prime. So it's exactly the same thing. For the backward pass, the derivative of your loss function with respect to a pixel, X is a pixel at location X prime and Y prime. And remember, you are not taking derivative with respect to X prime or Y prime. They are just indices. You are taking derivatives with respect to X. You're taking derivatives with respect to pixels, not pixel locations. There is going to be some transpose going on. That's going to happen all the time. And then there is going to be the derivative of your loss with respect to the pixels in your Y, okay? But this derivative, you are computing the derivative of loss with respect to X at location X prime and Y prime. But that location can be impacted by multiple inputs. And because this is your total gradient, you're adding those numbers up. All of these pixels from your Y, or derivative of your loss with respect to Y, are impacting the location X prime and Y prime. So all of these are impacting it. Now you can see the relationship. If you rename the derivative of L with respect to X prime, with respect to X, to be your new Y, and let's ignore the transpose. If you ignore the transpose, that is basically your Wij here. And this derivative is just your new X at these locations. So you're renaming X prime to be X. You're renaming the derivative of L with respect to Y to be the capital X, etc. You're ignoring the transpose. And this is basically your output derivative. So is everything clear so far? So there is a question, why do you have these twos here? These twos are because you want to be a little bit careful on the boundaries, and so don't worry too much about them. This is just to make the math work. On the boundaries, you could pad, you could not pad, but this is just to make this math work out. Because if you put, you want to know your pixel location, your value, your pixel values at, let's say, location 2 and 2, then this is going to work out pretty nice. 2 minus 2 is going to be 0. 2 minus 2 is going to be 0. And then you're going to have 3 pixels, pixel 1 and 1, 1 and 2, 1 and 3. And these are going to be a window around your pixel 2 and 2. Okay. So this is just for convenience, for the math to work out. Any other questions? So the idea is that fractionally strided convolution is not a new concept. We had to do it even when we were doing backpropagation through a simple convolution operation. We never saw it because TensorFlow or PyTorch is doing it for us. But It is basically the same operation. And it's going to help you increase your resolution from one layer to the next one. Okay, perfect. But in the end, I promise that I'm going to give you unsupervised representations for images. What can you do? You can look at your discriminator. Your discriminator is going the inverse route. So it's going from right to left. It takes an image and then it's going to downsize it. You can take, basically what you can do is you can take the last layer. That could be your features. In addition, each one of these guys, each one of these intermediate layers, you can take them as features as well. But if you do that, it's going to be a huge vector representation. And we don't like that. The objective was to reduce the dimension, not to increase it. So what you're going to do is you're going to pull these windows. So you're going to create a 4x4 window. Basically, you're going to say, I'm going to put a bunch of these pixels in buckets or in patches, and then pull them, just average pull them or max pull them. For instance, if you have here an 8x8, you want to create a 4x4 spatial grid. And I guess each spatial grid is going to be 2x2, and you're going to do a pulling on those 2x2 windows. If you have 16 and you want to create a 4x4 grid, each one of those grids is going to have a size of 4x4. And then you're going to pull that and turn that into a single vector. Now remember, you're going from right to left, and image goes in, and then you can just read off the features. That's going to give you a feature vector that you can now give it to a classifier, a simple classifier, maybe a logistic regression or a support vector machine. If you do that and you compare the framework to other previous state of the art, which are unsupervised, this is actually giving you good features. The features coming out of DCGANs plus L2 normalized support vector machine is going to give you an accuracy of 82.8 on CFAR10 images. Okay, and DCGAN is trained on Imagenet. And Imagenet is a big data set. It has 1 million images, and then it has 1,000 classes. CFAR10 is much smaller. It's 32 by 32 images, and you have 10 labels. Okay, so you can use your feature vectors to represent images. And these feature vectors are coming out of the discriminator part of your generative adversarial neural network. But what can you say about the Z's that you end up with for the generator? What can you say about them? Can you play around with Z and then some cool stuff happens to your images? Let's see. What is the objective? What can you do? We are doing addition, subtraction, and addition in the latent space. For instance, if you have a man with glasses, you can subtract a man without glasses. You can add a woman without glasses, and then you can look at the center image here. So that's going to be a woman with glasses. This was the final objective. This is actually what you want to do, but there is a catch. You cannot do it on any pair of images. It has to be done on average. So maybe you sample a couple of images. Now you're in your hidden space. On that hidden space, you're going to average. You're going to average, I don't know, 3 vectors. And now you take the average of the 3 vectors, you push them through your generator. That's the image of the man with a glass, with glasses. You do the same thing for the other guys. So you have to do it on the average. And then you do your operations in the hidden space, in the Z space. You add and subtract. And then you're going to output your images. Now the question is, what are these 9 ones? The center one, we know that it's coming out of this operation. The other ones are just, you can add noise to your Z. And then that's going to give you these other 9 numbers, nine faces, because this is a generative process. It's a probability. Does that answer your question?
I've got a quick question.
Sure.
Are we doing the subtraction and addition in the space of images, or are we embedding them all into the hidden dimension and doing the addition and subtraction in the hidden space and then passing that through the generator to get the images?
So no, these additions and subtractions are done in the hidden space, in the 100 dimension space.
That makes sense.
But then you take that and push it through your neural network. That's going to give you an image. Push it through your generator. And you know how to go from your 100 dimension space to the space of images using your generator. So you take these images, you go to 100 dimension, average them out, and then go back. That's going to give you one image. But then you keep the vector, the average vector that you came up with. And then
do-
you take that average vector, subtract it, add it, and then generate images out of it.
That makes sense.
Okay, perfect. So you can do cool stuff using both the discriminator and the generator. Any questions so far?